Thank you, Richards. Good afternoon to everyone. Good morning, good afternoon, and welcome to the Astronomy Department of the University of São Paulo. Thank you all for participating in this seminar. And today we are honored of having the presence of Dr. Ilaria Caiazzo, researcher at the Caltech, California Institute of Technology in Pasadena, US. And I'd like to share with you some information, some biographical information about Dr. Ilaria. She got her bachelor's degree in physics from University of Genova in 2011, and master in astrophysics from University of Milan in 2015, and defended her PhD thesis in physics at the University of British Columbia, Canada in 2019. And since then, she has been working as a postdoc researcher at Caltech, US. And next year, she will join the Institute of Science and Technology of Austria in Vienna as an assistant professor. Ilaria has experience modeling polarized emission in the X-rays of neutron stars and black hole systems, and she's interested in stars, in their lives, and in their afterlives. Dr. Ilaria, thank you very much for accepting the invitation, for giving this talk. And today she's going to talk about From Gaia to Lisa, White Dwarfs at the Center of the Stellar Revolution. You can ask it to Ilaria after her presentation or during her presentation. And if you are following the seminar via YouTube, you can also write down your questions in the chat, and I will bring it to Ilaria. And that's it. Ilaria, please feel free to start whenever you want.
Thank you very much. Thank you for the introduction, and thank you for inviting me. I'm very happy to tell you about my work on white dwarfs today. So I'll start from the basics because I know that a lot of people don't think about white dwarfs a lot. But white dwarfs are extremely common in the universe. They are the most common star corpses because more than 95% of all stars become white dwarfs when they die. And therefore, we know a lot about the typical white dwarf. So a white dwarf in a nutshell is a compact object, is the central core of a star, and it's about the size of about a mass about half the mass of the sun, but in a much smaller, more compact radius. The radius of a white dwarf is usually comparable to that of an Earth-like planet. And since, so as I said, they're just the core of stars, and so they're made mostly of the ashes of nuclear burning, usually carbon and oxygen. And they could be only made of helium if they're very low mass, or oxygen and magnesium for more massive white dwarfs. And as I said, they're extremely compact, which means that the gravity on their surface is extremely strong. And therefore, all the heavy elements sink very quickly. And so the atmosphere is just made of the lightest element present. So the surface you can see here, the typical white dwarf is made mostly of hydrogen. And so here you can see the spectrum of a white dwarf, of a typical white dwarf. And you can see that it has absorption lines of hydrogen only, the Balmer lines here, because this is in the optical. So as I said, we know a lot about this typical white dwarf because there's lots of them in the galaxy. But there are a lot of open questions about white dwarfs that have a lot of implications for a lot of fields of astrophysics. And they usually revolve around the atypical ones. One question that I'm very interested in that has a lot of implication is, what is the maximum mass for a star to actually become a white dwarf? Because as I said, like most stars become white dwarfs because most stars are low mass. And the limit for a star to become a white dwarf in mass is about 8 solar masses. More massive stars become neutron stars or black holes. But these 8 solar masses is not really well understood. It could be 10, it could be 7. And if you're interested in the production of neutron stars in the galaxy, the rate of core collapse supernovae, all of these rates depend a lot on where this limit is in terms of mass. And we still don't know it very well. Another question that I'm very interested in is magnetic fields. We know that a large fraction of white dwarfs are magnetic, and the fields in white dwarfs range from just a few kilogauss to 1 billion gauss. So there's a huge diversity in magnetic fields, and we still don't know where these fields come from. And that's also interesting because it has implication on the question, where do magnetic fields come from in stellar environments? And then there's the huge field of planets around white dwarfs. This is a very recent field, but it's become huge because in the past 10 years, we have discovered a lot of planetary systems around white dwarfs. We have discovered entire planets, partially disrupted planets, debris disks and rings. So these kind of systems are very interesting because they tell us what happens to a planetary system when the central star dies. Then I'm going to mention briefly also today about white dwarfs in binaries. Many stars evolve in closed binaries, and many of them become double white dwarfs. And these double white dwarfs will be the strongest sources when the gravitational wave observatory LISA will be launched. And so there's lots that we can learn about these. And then last but not least, the question of what are the progenitors of supernovae type 1a? We know that white dwarfs are involved in some way, but we still don't know what's the fraction of what's the contribution of mergers or just accreting white dwarfs to the type 1a supernovae. So lots of open questions. There's more, of course, out there. Just mention the ones that I'm more interested in. But this is the greatest time. This is a great time to study white dwarfs and to answer these questions, because there are a lot of new instruments and surveys that have recently come online or that will be functioning soon, and each one of them is amazing for the study of white dwarfs. One of them is Gaia, the European mission. I'll talk about this. Gaia has been incredible for a lot of fields of astrophysics, and especially for white dwarfs. But another class of new surveys that has really changed the way we study white dwarfs are the high-cadence time domain surveys, and I will talk about these. Then the spectroscopic surveys. There's several spectroscopic surveys currently undergoing, SDSS V, DESI, WEAVE, that are giving us spectra for millions of stars in the galaxy. And then, of course, there's LISA, JWST, eROSITA, and Roman is coming up soon. So I will touch on some of these missions, but what I want to say is that all of these missions are leading to a renaissance in stellar astronomy, and in particular in white dwarf studies. And I'll start with Gaia, because Gaia has really been revolutionary for white dwarfs. And because before Gaia, the only way to find a white dwarf was to point a telescope and take a spectrum. That is because white dwarfs are blue and faint objects, but unless you know the distance, it could be a much bigger blue star instead of a white dwarf. But Gaia has given us precise photometry and astrometry for billions of stars. And distance is to billions of stars. So here you can see the Gaia HR diagram with color on the x-axis and absolute magnitude on the y-axis, because we have the distances, so we can plot them this way. And so when you have the absolute magnitude on the y-axis, then the white dwarfs are all there in the lower left corner. And that's how you can find them and identify them. So before Gaia, we had only a few thousands, like about 30,000 white dwarfs. They came mostly from this lone spectroscopic survey, which was not designed to find white dwarfs, was designed to find galaxies. So the white dwarfs that we knew before Gaia were mostly like the leftovers of the SDSS survey. And they were very non-homogeneous, quite biased and quite shallow sample, as you can see up here. And down in the lower plot, you can see after Gaia DR2, which was the first big release of Gaia, we went up to about 300,000 white dwarfs, and it was a much, much deeper, much more unbiased sample. So we now can see white dwarfs all over the sky. And this has really changed the way we study white dwarfs, as you can imagine. I'm gonna just mention one project that I have just by using Gaia, and I'll show you how it has already improved a lot our understanding of white dwarfs. So this project is about finding white dwarfs in open clusters. So open clusters are these clusters of stars that were all born at about the same time. And they're, before Gaia, we could just identify them because they were all in the same region of the sky. Here you can see the Pleiades. But with Gaia, we have parallaxes and proper motion. So we have the distances of all of the stars. And on top of them, we can see how they move in the sky. So you can identify members of clusters very well, because not only you can find all of the stars that are in the right place of the sky at the right distance, but you can also see how they're moving. So if you have a star that is moving in the opposite direction of where the cluster is moving, even if it happens to be close to the cluster, it's probably not a member, but it's just passing by. So Gaia has given us the possibility to find very high confidence members of open clusters. And why is this important for white dwarfs? It's because, as I said, in open clusters, all stars have the same age. And you can measure the age in open clusters quite well. Here, for example, you can see the HR diagram of, again, the Gaia HR diagram of 3 different clusters of 3 different ages. And you can see that we can measure the age of the cluster just by looking at which stars are turning off the main sequence. And here in particular, we were measuring the age of this black cluster, which I think is ACC 47. And we measured it to be about 90 million years plus or minus 5. So you can get a very precise age of the cluster itself, so of all the stars in the clusters. And this cluster also has a white dwarf, as you can see down here. And so you can take the white dwarf and take a spectrum of the white dwarf, and you can see how old is the white dwarf itself, since it was born as a white dwarf, so its cooling age. And by subtracting those two, you can figure out what was the progenitor mass of that particular white dwarf. At what age did the progenitor evolve off the main sequence? And this is the only way we can find white dwarfs for which we know what the progenitors are, and it's the only way in which we can constrain the relation between the initial mass of the progenitor star and the final mass of the white dwarf. And you can see, so here in this plot, I'm showing you this relation. On the y-axis, the final mass of the white dwarf, and the x-axis, the initial mass of the progenitor stars. And here I'm only showing this non-white dwarfs above 2.5, with a progenitor above 2.5 solar masses. And you can see that just using Gaia, just in the last couple of years with our group, using this method of identifying white dwarf in classes with Gaia, we have looked at and found a lot of the high mass white dwarfs and really constrained the high mass end of this initial final mass relation. And on top of that, we are starting to constrain that maximum mass for a star to become a white dwarf. And this is all work that has been done just using Gaia. And so what we are doing now is this, also another thing that you can do, also by just using Gaia, is going back in time. You have a cluster, and you can look at the volume around the cluster, and you can go back in time because you know how the cluster moves and how it moved in the past. And so you can go back in time and look at the stars around the cluster and the cluster itself and find stars that are not in the cluster anymore, but that escaped the cluster. And this is what we've been doing. So you can reconstruct the history of a cluster going back. Here, for example, is the cluster Alpha Per, in which you can see the main sequence. There's no white dwarfs right now in the cluster. But if you go back in time, this is stars that escaped between 0 and 25 million years ago. You start finding some white dwarfs that escape the cluster. And this is very important because the most massive white dwarfs are very easily escape clusters. Clusters are very loosely bound. And this is how you can find more of those very high mass white dwarfs to constrain the initial final mass relation. And this is what we're doing right now. For example, we looked at a very close by cluster to Earth. The Hyades is a very famous cluster, very well studied. There's a lot of white dwarfs in it, but none of them are particularly massive. And so where are the massive white dwarfs? Hyades is a very rich cluster. You would expect a lot of massive white dwarfs to be in the cluster, but they're not there. So it means that they must have escaped. And therefore, and so we use this technique of going back in time and finding escapers from clusters. And we found 4 ultramassive white dwarfs that escaped the Hyades. And this is all work in progress, including an extremely massive white dwarf very close to the Chandrasekhar mass. So I've just been talking about Gaia. I'm going to skip a few slides because this is all other stuff that we have been doing just with Gaia. But I'm going to move forward because, as I told you, I want to tell you about what we can do with a lot of these new facilities. And of course, I cannot not mention JWST because everyone right now is using JWST. And JWST has been incredible in studying, from clusters of galaxies to tiny planets around stars. And it's also a great facility to study planets around white dwarfs. And I have, there's been a lot of work in this section, in this regard. And I have several projects with several people. But I just want to tell you about one project that I'm working on right now that I'm very excited about, which is using JWST to find the first planetary systems in the galaxy. Because, as you know, we still don't really know when was the galaxy first forming planetary system. Is there a minimum metallicity required for planetary systems to form? Was there a certain time where the galaxy started forming these planetary systems? We still don't know. And the way to answer these is to look in globular clusters, because globular clusters host the oldest and more metal-poor stars in the galaxy. And so one way to go at it would be to look for transits in globular clusters, which has been done, but not very well. I think there's a lot of space to look for transits of planets in globulars. I think we can, it's still an open question if it's doable or not. But another way is to look at former planetary systems around dead stars, also around white dwarfs. Because white dwarfs in the field, not in globular clusters, but a lot of white dwarfs have been seen to have debris disks around them, like you can see in this picture, of material falling onto the white dwarf, so maybe asteroids or planetesimal, that accrete on the white dwarf and form a debris disk around it. And this is shown as an infrared excess around the white dwarf. So here you can see a spectrum energy distribution of a white dwarf. On the blue side, you can just see the white dwarf, and you can see that the spectrum of the white dwarf would go down in the infrared because these are pretty blue objects. And then you see an excess on the infrared side, which is given by the presence of the disk. And as I said, this disk is evidence that there is a planetary system around the white dwarf, because this disk is made of some sort of planetary material falling onto the white dwarf. And therefore, one thing that we can do with JWST is look into globular clusters and see if there are these white dwarfs with infrared excesses in globular clusters. That would tell us that there are ancient planetary systems in globular clusters. And that's what we did. We proposed to look for, to take a JWST look at the globular cluster 47 Tucane. Here you can see the field that we chose. This is the center of the globular cluster, which was a field a little bit on the outskirts. We chose it for several reasons that I can go more into it. But one of the main reasons is that this particular field has been observed a lot with HST, with the Hubble Space Telescope. It has the deepest observation, 121 orbit of HST in just this one field. So we know where all of the white dwarfs are in that field, and we know their masses and temperatures, and so we can easily identify any infrared excess because we know what they should look like in the infrared. So, and this is the planned observation with JWST. We got these 3 orbits a few months ago. The 4th orbit, there was a problem. So it was actually just observed last week. So this is all very much work in progress. I do not have the results yet. I wish I would, we might have found excess on a white dwarf, but it's still all early. But I just want to show you how beautiful the images are. This you're seeing at the blinking between the HST image and the JWST one. The JWST is the spiky one because of the ugly PSF of the hexagonal mirrors. But you can immediately see that, here I'm comparing more than 100 hours of HST versus 5 hours of JWST. And you can see that we're already going deeper. You can see galaxies showing up. You can see stars popping up from nowhere. So it's really an incredible data set. I wish I could show you some results, but the results are coming probably in a month or two. We know where all the white dwarfs are, and so if we find some with excess, that's going to be proving that yes, planetary systems of some sort existed already 13 billion years ago and such low metallicity. If you don't find any, it could be an indication that the galaxy was not ready to have planetary systems yet. That there was another science case for this proposal, which was to find for the very first time, brown dwarfs in a globular cluster. Because here you can see the HST image of those 121 orbit. It goes very, very deep. You can see it got to the end of the main sequence, but it did not reach the brown dwarf sequence. But with JWST, we should be able to reach the brown dwarf sequence. But I'm going to skip this because I don't have that much time. You can ask me about it if you're interested. Because now I want to continue in my tour of great facilities to study white dwarfs, and I finally want to tell you about the time domain surveys, and in particular about the Zwicky Transient Facility. So the Zwicky Transient Facility is an optic survey that is run by Caltech. It's on this tiny telescope, the 48-inch telescope at Palomar. And the principal investigator is Sri Kulkarni. What it does is that it takes images with a very big field of view in 3 filters, G, R, and I. And you can see here the huge field of view of ZTF is 47 square degree. Here you can see compared to the Andromeda Galaxy or the Moon and to other past or planned missions. the fact that it has such a huge field of view, it means that it can cover and take images at a very high cadence. So ZTF right now is looking at the entire northern sky every 2 nights. So for every sources in the sky, down to about 21st magnitude, we have light curves. So we have images with the cadence of a couple of days, now up to 5 years. So this is amazing if you want to find transients, so things that blow up in the sky, because you can find them very easily very quickly. And so this has been amazing for finding supernovae, TDs, all type of transients. But it's also incredible for stars that vary with time, because you can get all of these epochs and you can search for stars that vary with a certain periodicity. For example, here I'm showing one star. Actually, this is 2 stars. It's a binary it's a binary of 2 white dwarfs that eclipse each other every 7 minutes. And here you can see the light curve. This is not the ZTF light curve. This is a light curve taken by staring at these objects for half an hour, 40 minutes or something, with another telescope. But we did recover it with ZTF, because you can just search for periodicity in the 5 years light curve, in the 5 years database. Of course, this requires a lot of machinery and software to do so. It's not that easy, but we did. And now we can find variable stars and binaries and all type of variable objects down with periods down to just a few minutes, like this one. And you can do a lot with this type of data. The part that I'm most interested in is finding the endpoint of mergers. So as you know, lots of stars live in binaries, and if they're both stars are less than 8 solar masses or something like that, they do become white dwarfs. And if they're close enough, the 2 white dwarfs can emit gravitational waves and merge, similar to neutron stars or black holes detected by LIGO. And when they merge, if the mass is high, then they explode in a type 1a supernova. And so mergers are known to be, at least in part, progenitors of type 1a supernova. But if the mass is not high enough, the merger might actually result in another white dwarf. And the white dwarf that we expect to be the result of a merger has specific characteristics. So on average, they're more massive than the other white dwarfs, because you're taking 2 white dwarfs and merging them. And they are rapidly rotating, because you have the orbital angular momentum of the binary. The sum of it is transferred to the final object. And so you expect the white dwarf to be rotating fast. And on top of that, you expect them to be highly magnetized. And that is because during the merger, there's very strong dynamos that develop and that can enhance the magnetic fields to very high magnetic field strengths. And so if you have something that is magnetic, often the magnetic field can modify the emission from the surface and make it not uniform, like you can see here in this cartoon animation of a magnetic star. And so if you have something that is not uniform and it's rotating, maybe it has a hot spot that is coming in and out of the line of sight, that means that the star is periodically variable. You can see the luminosity going up and down with the period. Therefore, we can find them using ZTF. And that's exactly what I've been working on lately. This is the search that we did. I was focusing mostly on the most massive. Here you can see a white dwarf HR diagram. These are like all white dwarfs within 200 parsecs. And the different lines are different evolutionary tracks for different masses. And down here, the fainter and bluer ones are the more massive white dwarfs. That's where I focused my research, my search mostly, because we expect a lot of massive white dwarfs to be merger remnants. And so we looked in ZTF and we looked for periods, and we found lots of them to be photometrically variable. Here you can see one light curve found in ZTF, and then here a better light curve with follow-up photometry. And we also took spectra to figure out if they were magnetic. Now, if you're interested, you can ask me about this. I'm going to skip this because I don't have much time. But from the spectrum, you can understand if a white dwarf is magnetic or not. And I can tell you during the Q&A if you're interested how. And so we did this search, and this was the very first object that we found. It was one very blue, very dim white dwarf down here. It was one of the bluest objects in Gaia. Here you can see a pan-star image of the star, very, very blue. So it really stood out because of that, but also stood out because it was varying with a period of only 7 minutes. Here you can see the light curve. And 7 minutes is very short. Normal white dwarfs rotate with periods that go from a few hours to a few days, usually. So 7 minutes is very, very hard to get with normal stellar evolution from a single star. So this was already very interesting. We took a spectrum of the white dwarf, and I did not explain you how we can see that, but we could figure out from the spectrum that this white dwarf is extremely magnetized. It's 100 megagauss. The magnetic field is 800 megagauss, which is a lot. It's almost a gigagauss. It's overlapping with the fields of millisecond pulsars, just to give you an idea. And on top of that, we looked at the radius of this white dwarf. We got some UV photometry to look at the SED and measure the radius of the white dwarf. And we realized that, I told you most white dwarfs have radii of the size of the Earth, about 7,000 kilometers or something like that. This white dwarf has a radius comparable to that of the Moon. It's a very, very tiny white dwarf. Radius about 2,000 kilometers. And so here, So here you can see the white dwarf and compared to the Moon. That's the real size of the white dwarf. And so it's extremely small, which for a white dwarf, white dwarfs are degenerate. They're kept up by electron degeneracy pressure. So the more massive they are, the smallest they are. And therefore, this is the smallest white dwarf ever observed, which also means that it's the most massive white dwarf ever observed. It's very, very close to the Chandrasekhar mass, or the maximum mass for a white dwarf before it explodes. It's so small and massive and dense that inside its core, there is some electron capturing going on. So it's so dense in the core that electrons are captured on nuclei of sodium and converted into neon, which is something that happened, for example, when you are in a proto-neutron star, at the end of a core collapse supernova. That's all this neutronization that happened in the neutron star. It produces a lot of neutrinos. So this white dwarf is so dense that there is a little bit of that happening in the core. So I'm almost out of time. So I will just want you to, let me tell you about this. So that was the first one. This very interesting object. And right now we have a big sample, about 70 candidates with a big range of temperatures and magnetic fields. And this is a great sample because on one hand, it's great to study magnetic white dwarfs because it's a very interesting sample of magnetized white dwarf. It's great because it can help us constrain the pathways that lead to mergers. And from this sample, we can constrain the merger rate in the galaxy. So so these are the white dwarfs that, didn't explode, right, in type 1a supernova, but barely. because they're very, very massive. And so they can tell us what's the rate of the ones that actually explode in type 1a supernova, which are the ones that are slightly more massive. And so we are working on this, and this sample is still not published because I'm trying to get a good sense of the selections effects in ZTF and figure out like really what's the rate, how many am I missing, and what's the real rate of mergers that produce this type of objects. But it's coming out soon. And before I conclude, I wanted also to, oh no, I still have a lot to talk about, but it's been already talking about 40 minutes. I wanted to talk also about binaries. There's a lot of things that you can do with ZTF and binaries. And with our group at Caltech, we've been finding a lot of very interesting objects. Here you can see, so if you look at the evolution of closed binaries, you know, you have like the mean sequence stage, then one of the stars evolve, and you have common envelope, and out of common envelope, you have one becomes a white dwarf, and you can have like cataclysmic variables, etc., etc. And like what I wanted to say is that at each stage of this closed evolution in binaries, you can have the stars to be variable because maybe they're eclipsing, or because they are, you know, they have modulation due to their binarities, or they have accretion. And so thanks to ZTF, these are light curves that we have found of objects at each stage of this evolution. And these are just from ZTF and just from our group at Caltech. So you can see the possibilities here. Just using these time domain surveys, we can find big samples of objects at each stage of binary evolution, and therefore connect the dots and really understand the evolution of stars in closed binaries. And you know, I've told you only about ZTF, but there's lots of other time domain surveys. There's TESS, which is, you know, in space already, and it's been taking data for like several years now. Then there's lots of planned ones that are starting right now that are similar to ZTF, but in the south. You know, LS4 and Black Gem, Atlas just released the south. And these are all time domain survey. Gaia itself is going to release light curves soon. And then, of course, in, you know, I think a couple of years from now, we'll finally have data from the Vera Rubin Observatory, which I'm sure you have heard about, LSST, which is going to go so much deeper than ZTF, and it's going to allow us to discover a lot more of these objects. So this is a very exciting time. And as I was telling you at the beginning, right now there's a lot of like spectroscopic surveys going on. They are taking spectra of objects all over the sky. So millions of spectra of stars, and including white dwarfs all over the sky. And so putting together the time domain surveys with spectra, we can really find and classify a lot of these variables. You know, I was mostly focused at the end stage of binary evolution, the double white dwarf mergers, but there's lots that we can do to understand the entire evolution of white dwarfs and stars in binaries. And so this is a very exciting time. So I think that when we actually get to LISA, which is this gravitational wave observatory in space that is going to discover all of the binary white dwarfs in the galaxy, we will have, in 10 years from now, when LISA comes up, we will have understood a lot about binaries and white dwarfs in binaries. So this is like, I'm going to skip these. So I'm skipping a lot because I didn't realize it was only 40 minutes. I thought it was like 50. So I'm skipping a lot of slides. So before I conclude, I just wanted to tell you about one more incredible object that I found using ZTF. It really shows that when you uncover a new way to study stars, you find a lot of very strange and interesting objects. This in particular, I found it because I was looking for merger remnants. And these look like one of those. You know, it has a 15-minute period. It's a massive white dwarf, around 1.2 solar mass. It has a 15-minute period, and here you can see the light curve is pretty sinusoidal, quite similar to all of the other ones that I've been finding for mergers. And therefore, I took a spectrum of the object, And this is what it looked like. No sign of obvious magnetism, but you can see that there's like very shallow lines in absorption that are both of hydrogen. The blue ones are hydrogen and the red ones are helium. So this looks like a mixed atmosphere, hydrogen and helium white dwarf, which is not particularly strange per se, but this that you're looking at is the phase average spectrum. So it's a long exposure that covers several periods of the white dwarf. Then I decided to go and take phase resolved spectra, so take a different spectrum at each rotational phase of the white dwarf. And this is what I found. Here you can see again in blue, there's the hydrogen lines, and in red is the helium lines. And you can see these are different rotational phases. So you can see that on one phase, for example, up here, I don't know if you can see my cursor, but like in the upper one, the hydrogen lines, the blue ones are very strong, while the red ones, the helium lines, are absent completely. And if you go to the opposite phase, the hydrogen lines have disappeared, and the helium lines are there and they're strong. So what it means is that this is a double phase white dwarf. On one side, it's made of hydrogen, and on the other side, it's made of helium, which is quite exotic object. And as you can see here, we nickname it Janus, like the Roman god with two faces. And this could be a very appropriate name because Janus is also the god of transition. And so maybe this white dwarf is actually transitioning from having an atmosphere made of only hydrogen to an atmosphere of only helium. And we might have catched it as this is happening. And that is because, so again, here you can see the HR diagram for white dwarfs. You have up in the upper left, you have young hot white dwarfs, and then they go down to the lower right part as they cool down. So they follow these lines. And what happens is that here, where the blue highlighted region is this range in temperatures where there's very few helium-dominated white dwarfs known. Most all of the ones known in that region have hydrogen atmosphere, not helium. And then you see, as you go down here, like the pink dots are helium-dominated white dwarfs. As you go past that lower edge of this gap, all of a sudden you have helium white dwarfs. This means that some hydrogen-dominated white dwarfs are bound to transition into helium-dominated white dwarfs. And I think what in Janus is this strange double phase white dwarf is right at the lower temperature edge of this transition. I mean, the reason why we think this transition happened is because even if you have a tiny amount of hydrogen, it's enough, to float. Hydrogen always floats. It's enough to cover the entire surface, similar to water on a mountainous planet. You can just, even if it's tiny, you can just spread it all over. And even so, I think this is what happens at high temperatures, that you have the hydrogen floating up and covering the entire surface. But then when you hit around 30,000 degrees, which is where Janus is at, you have convection starting in the helium layer right underneath the hydrogen. And that convection destroys this thin hydrogen layer. And that's how you have some white dwarfs transition to have just helium atmosphere, because the helium is so much more that it completely dilutes the hydrogen and the hydrogen disappear. And maybe Janus that's what's happening there. And if you have a little bit of a magnetic field that is not homogeneous on the surface of Janus, is a bit stronger on one side than the other, the stronger magnetic field might inhibit this convection, and therefore we still see hydrogen. And where the magnetic field is weaker, the convection has started and has destroyed this hydrogen layer. I mean, this is a possibility. This is the first object that we found of this type. So we have some ideas of, this is one of them, of what could be causing this strange nature of the object. But again, this is just the first one. Finding more of them will help us understand what's really going on. And indeed, we already found several others, always using ZTF. This is another example of a partially double phase objects. And so there's a lot more to be found. And so I'm gonna conclude here because I'm way out of time, and I'll ask for questions.
Thank you, Ilaria, for the very interesting talk and for making this very didactic. We'll open now for questions. I'd like to start. So we have some questions from auditory. I will first make a question by Professor Kepler. He put during your talk in YouTube. I will read it for you. It's when it's about the cluster 47 Tucanae, when you show with the JWST images, are you going to search for massive, very cool white dwarfs, or only the ones identified previously with the Hubble Space Telescope?
That's a very good question. Thanks, Kepler. Yes, so the ones that we already know with the Hubble Space Telescope are the easier to find, because we already know them. We will try to get to massive cool. Actually, one of the collaborators on the proposal is Pierre-Emmanuel Tremblay, and he's very, very interested in like ultra cool white dwarfs. And we have, we are going deep enough to see, massive and ultra cool white dwarf. The biggest problem will be distinguish them from the background SMC. Because unfortunately, 47 TAC is in front of the Small Magellanic Cloud, and therefore, exactly where the white dwarfs are like red and cool, that's where you can have some contamination from the SMC. So we will try. Also because we might be able to remove the SMC with proper motions, but we still have to get there. As I said, we're still working on the data. But yes, that's a very interesting part. And I hope we will get them.
Thank you, Ilaria. Now, a question by Camila.
Hi, thank you very much for the interesting talk. I learned a lot. And I was very curious, so can you explain how do you know about the magnetic fields by the spectrum, please?
Sure. Yeah, I had to skip that because I was like way, behind. I find that when I talk on Zoom, I talk much slower. I don't know. I always fall behind. Let me show you. Let me just share my screen quickly again. Okay, and I think, let's see, we'll be here. So I showed you this is like the normal white dwarf spectrum, right? With absorption lines of hydrogen. This is non-magnetic, okay? When you have a magnetic field, what happens is that, these are the electron in the hydrogen atom is jumping from a level to, from a level to a higher level, right? And it's absorbing the energy. For example, this is n from 2 to 3 or 2 to 4, etc., right? But what happened with the magnetic field is that these levels are not degenerate anymore. So if you remember from quantum mechanics, you have the levels, you have different quantum numbers, and in particular, you have the M quantum number, the magnetic quantum number. And the levels are the same if delta M is equal 1 or -1 or 0. But with the magnetic field, that's not true. The energy it's slightly different. The energy in the jump is slightly different. Is delta M is equal 0, +1 or -1. And therefore, you see that the absorption lines is not just one at a certain energy, at a certain wavelength, but you have 3, because you have the delta M +1 or -1 or 0. And how separated these 3 lines are depends on how strong the magnetic field is. So you can see here, that they're getting more and more separated in these three different objects because the magnetic field is higher, right? And that's for like intermediate magnetic fields, about from 1 to 10 or 30, 20, 30 megagauss. And then if you go to even higher fields, you can see here, this is again, on the y-axis, you have magnetic fields. I don't know if you're seeing my cursor, but on the rightmost plot, you can see it those are where you would expect the lines depending on the strength of the magnetic field. And at lower magnetic field, you see this splitting. But if you go to higher and higher magnetic fields, it becomes more and more complicated. You have more degeneracies get lifted. And so you have all of these components all over the place. But we can still identify some of them. And so you can see, for example, here in the middle plot, there's higher magnetic fields one. And so the way we identify them is with these spaghetti plots, right? So we look at where the lines should be depending on the magnetic field, and then we identify them, identify the field by identify the different lines. Is that?
It was very clear. Thank you very much for the explication.
Oh, thank you, Ilaria, for this very interesting talk. I was curious about the mechanism for segregating the high mass white dwarfs in the IAGs. It is related to some dynamic in the cluster. What is the source of this segregation that ejects high mass white dwarfs?
So you have to think about globulars are very bound, right? Open clusters are not very bound at all. If you're going at a speed of maybe 1 kilometers per second, as low as 1 kilometers per second, you can escape the cluster. And therefore, so at one point we don't see enough massive white dwarfs in the clusters, and that's a hint that many of them escape. But also you can imagine when you have a massive white dwarf, like a 1.2 or 1.3 solar masses, the progenitor is about 5, 6, 7, 8 solar masses. And so we're talking that at the end of its life, it's going to lose several solar masses winds. And so even if there is a little bit of asymmetry in these winds, you can get very easily a kick. And here we're talking about very small kicks, 1 kilometers per second.
Oh, I see.
It's very easy to achieve.
Yeah, I see. Another curiosity is about the genus object. Do you get different temperatures if you use the helium and hydrogen lines?
So we did. So I got swift photometry in the UV to try and constrain the temperature, and so I got phase resolved. So you have photometry both in the optical and the UV, and it's phase resolved. So I have the two SED moving. And so I fitted the hydrogen line, the hydrogen side with hydrogen and the helium side with helium. And so they're consistent to have the same temperature within the error, but the errors are big, of course. So they could be that the difference is just a difference in composition. There could be a difference in temperature too, but I'm just fitting models to SED. So the problem is that the lines themselves are very weak. Which is often seen in magnetic white dwarfs, that the lines are way too weak for that's why I'm thinking also it's magnetic, because if you look at the SED, it looks like, again, it's a 35,000 degree white dwarf. But if you look at the lines, they're so weak that they seem like a 50,000 or even more degrees. So there's no agreement there. So I'm not sure what the real temperature is. I think it's 35,000 because if it was really 50,000 or more, you would see helium too, right, which we don't see. So I think the reality is that it's really around 35,000, but the lines are weakened by a mixture of composition, the fact that it's different composition, and some effect of the magnetic field. But again, this is very open.
Very interesting. Thank you.
Hi, I also want to thank you for this nice presentation. Congrats on these great results. I had a question on the magnetars. These are very strange beasts, and their formation and the origin of these extreme magnetic fields are still uncertain. And I was wondering if the most favorite scenario or pathway to make them is binary mergers, or if there are other mechanisms that are still possible, and whether this time domain service that you mentioned and you're working on can help us to pinpoint which is a mechanism that is forming them.
So you mean like the magnetars as like a highly magnetized neutron stars?
Yes, exactly.
So I think currently it's still the most I think the most accepted theory is like it's still people still think that it comes from core collapse supernovae like other neutron stars, but there's some of them tend to be more magnetic. I don't know if there is I've been a bit out of the loop of like magnetars and how they form. I don't think there's any theory on that they actually come from mergers. I mean, the merger of two white dwarfs can create a neutron star if the actual object collapses, but it would create a normal neutron star. If you look at the magnetic fields that I have on the mergers of white dwarfs, those magnetic fields, if you conserve the field and make them collapse, you would get to normal pulsars, maybe 10 to the 13 megagauss or something like that, 10 to 13 gauss, those type of fields. So if you're thinking about a merger of white dwarf creating a neutron star, I mean, it is a possibility that people have been thinking, especially in globular clusters. For example, globular clusters have young pulsars that people don't know where they come from because globular clusters are old. Pulsar, where are they coming from? And so people are suggesting that they come from mergers, but those are normal pulsars. If you look at the fields that we find in white dwarfs and you move them to neutron stars, you find normal pulsars. So I wouldn't say that magnetars come from mergers of white dwarfs. It would be probably something to do with the supernova or some special stars or special supernovae. I don't know.
Yeah, the second question I had was on your white dwarf, massive white dwarf, on whether what are the chances that it will collapse, and will that make it a magnetar, or will that make it a very, I don't know, normal neutron star, because it has a very high magnetic field. So that's why this triggered my question on the magnetar.
Yeah, I went very quickly on that. So for that one is an example. If you collapse that one, like the moon-sized white dwarf, you get a field of about 10 to the 13 gauss. So normal pulsar, and a period of about 20 milliseconds. So a normal young pulsar. So nothing strange. The chances of it to collapse. So right now there is electron capture going in its core, and so if you're removing electrons are what give support to the star, right? White dwarfs are kept up by the electron degeneracy pressure. So if you're removing them, the radius keeps shrinking, and you can get to a density in the core when you start having double electron capture on magnesium, and then once you reach on capture on sodium, it has to collapse. And so this can happen. This is happening right now because it's a young white dwarf, and it's still all mixed, but there's a lot of sodium falling, sedimenting into the core. Because of the high gravity. And so the more and more sodium sediments, the more of this process can go on until it can actually reach an instability. And the time scale for these, we are talking about hundreds of millions of years. That's a time scale for sedimentation. But that's also a time scale for crystallization. And so if the white dwarf actually crystallizes, there would be no more sedimentation, and so there would be no more, there would be no collapse. So I would say that the chance of this one actually collapses are pretty low, because I think it would freeze first. Also because it's with this neutrino emission, it's cooling much faster than normal white dwarfs. So it might crystallize even faster than normal white dwarfs, and so I don't think it would collapse. But it is a possibility, and since we have found this one, there might be more massive ones out there that will collapse. And if you just merge two white dwarfs that are slightly above the Chandrasekhar, then they will collapse, and they might either explode in a type 1a or create neutron star.
Very, very cool. Well, the timescales will be too long anyways, but the prospect is very cool. Thank you.
Thanks.
No, Betty, please.
Hi. Very nice talk. Thanks. Very interesting, amazing results. And I'm Elizabeth. And I have 3 questions, if I may. One question regards this last object that you showed, that has this asymmetry, with the emission, and then you have half of the star with hydrogen and with convective layers, strong convective layers, and the other one possibly not. So I was wondering if this could be connected somehow, as you suggested, with a magnetic field, but this would imply an asymmetry in the magnetic field distribution, and therefore this could be related to dynamo action, right? And then I was thinking about, do you have an idea of the period of the magnetic activity in this source? The reason that because I'm trying to figure out what kind of magnetic field distribution could lead to this asymmetry, right? So what is the direction of the rotation axis with regard to the asymmetry distribution? Because this is directly correlated with the magnetic axis as well, of the dipole, the large scale structure, and in order to try to figure out if this would be possible as a transient effect in the middle of the dynamo period, of the dynamo process. So do you have an idea on the...
Okay, let me answer like one or the other. So we did invoke magnetic field to explain this because, white dwarf are gaseous object. It's very hard to have this very stable configuration in which you have like one side, there is one composition, the other side is...
of course, it should be
you need something that to create this homogeneity and to keep it stable. So this white dwarf I've been looking at for years now. It's been like the last time, the first spectrum I took was several years ago, and the light curve has been completely stable for like 5 years. And the light and the spectrum also never changes, it's always the same. So it's a very stable configuration. And you have this separation of elements, and so you need something to create these. And so that's why we thought, we need magnetic field to explain it. Of course, since we are seeing this completely hydrogen on one side and completely helium on the other side, it has to be that if this inhomogeneity is due to magnetic field, then it's a pretty special geometry. It has to be not 90 degrees from the rotation axis, but a big angle, maybe 60 or 70 or 80 degrees from
multiple configuration. Multiple configuration.
It could be that we have like, I don't know, this the entire surface made of helium plus a large spot. It has to be a large spot of hydrogen. It doesn't have to be an entire space, like an entire hemisphere, but it has to be a large spot because otherwise we would see the helium. And so it has to be a large spot, and it has to be facing at us. Not exactly, it could be a little bit higher, a little bit lower, but it has to be, almost an orthogonal rotator. So that's
the rotation axis should be towards our line of sight?
No, the rotation axis is probably like, maybe not 90 degrees, but like a high angle versus
a high angle,
and the magnetic field should be towards the line of sight.
Right.
This is a special geometry, but it makes sense because, this is probably a very rare object. It's quite far, it's 400 parsecs away. All the other ones that I found don't show this extreme variation. I mean, I found some that in which maybe the helium disappears, but the hydrogen is always there, or vice versa, which makes sense because you need a very special geometry to just see that completely disappear. So this is a special object just because of geometry. All the other ones, they never completely disappear, one of the two elements, which makes sense, they're less special geometries. So that's why that's the kind of like geometry we're thinking about. Unfortunately, we cannot constrain it better than that.
Right.
In terms of angles, but yes, that should be the geometry. In terms of magnetic field strength, it has to be less than about a megagauss. Otherwise, we would see a splitting in the spectrum. So we're talking about maybe a few hundred of kilogauss, maybe a few tens of kilogauss. We don't know.
But well below the maximum expected in white dwarfs, like 10 to 8 Gauss. So you were expecting 10 to 6.
White dwarfs have shown magnetic fields from as low as, a few Gauss, sorry, kilogauss, to as high as 10 to the 9 Gauss, right? A gigagauss. So, and we've seen all of these in white dwarfs. What we see is that the field is very stable in all of them. So it's a big structure. It's not like in the sun where you have like all of these like spots going up and down and disappearing and reappearing. All of the white dwarfs that I've been finding, the light curve
largest scale field of this order, 10.
It's a large scale field, and it's like well structured. It's often not a dipole. It's often an offset dipole or things like that. And it's not like in this case, for example, for Janus, you need this field. If you want to explain it with the convection being inhibited by the magnetic field, you would need the field to be stronger on one side only and weaker the rest, which is something you can do with an offset dipole, for example. That could be a type of structure. In terms of dynamo, in terms of dynamos, I don't think the magnetic field is being created right now. So all of these white dwarfs have fields that are stable throughout their lives. They're not created. I mean, there's been a lot of like discussion about maybe magnetic fields are created within the white dwarfs, but we're talking about much colder white dwarfs, and we're talking about crystallization. This one is hotter, and so I don't think that the magnetic field must have been there since the beginning.
There is no possibility that it's a binary, a closed binary system. There is no possibility of this sort.
No, for several reasons. The period is 15 minutes, so you would see Doppler shifts in the line, which we don't see. The light curve, the light curve would have been like an eclipse, right? You would have like to have the two white dwarfs.
Of course, but
the light curve is just a sinusoid. So that's the first thing I thought. This must be true,
of course.
But it's not. Yeah.
And talking about binaries, do you have statistics enough from your data about the number of how frequent white dwarfs appear in binaries? Because and then you have this issue of these binary systems eventually because of the asymmetry producing gravitational waves, and if those waves are within the sensitivity of LIGO, Virgo, and
well, there's a lot of work in this sense. I'm not an expert, but with the launch of LISA 10 years from now, people have been thinking about this a lot. There's been a lot of studies. I don't have the numbers on the top of my head, but yeah, there's been a lot of studies for predicting how many binaries you will detect. It's not LIGO because it's a lower frequency, so it's LISA that is going to be launched 10 years from now. And yes, it's going to be detecting lots and lots of binary white dwarfs. My friend Kevin Burge, he works on binary white dwarfs, and with using ZTF, he has found a lot of them that will be very bright sources in LISA, or very loud sources, I guess, in LISA. Like the 7-minute binary that I was showing, that one is so close that it's emitting, and you could measure the gravitational radiation already, because you can see the period going down. You can measure the period decreasing as they get closer, and from that you can measure the gravitational waves emission, and it makes sense with GR and everything. So yeah.
Right. Very interesting. Thanks. And finally, just to mention that. Okay. I think I took too much of your time because I had another question, but it's okay. Okay, Rinaldo, you may go ahead, because I'm sure that there are otherwise.
Okay.
Thanks again.
Okay, there is a question from someone who is following in YouTube, Larissa Luciano. She says, in the new example of a star similar to Janus, that appear to have a magnetic field splitting the hydrogen lines. The effect is not observed in the original Janus. If you could explain this. And then next, also there is a question by Chico Jablonski. Maybe he wants to ask directly.
Let me think. I think I've already answered that one.
Yes, I think talking with Betty.
Yeah.
And
So let me just tell about the. So first of all, very good catching that. I mean, like it went so fast. People are really paying attention. Indeed, this new one that I found showed splitting. So that one, it's maybe I can show it again so people can actually look at what I'm talking about. Wait a minute. Can you see?
yes.
So, okay, this one is another one that I think it's similar to Janus, but of course different. You can see that it has, here is the hydrogen line, it's H alpha, and you can see that it's splitted. And here it's a helium line, also splitted. And you can see that at the opposite side, the helium line disappears. So this could be another Janus-like object. But another thing that happens is that the splitting disappears too. And so you get only one hydrogen line on the opposite side. So what's going on here is that possibly, so the splitting at this side indicates a field of about 8 megagauss. So what might be happening is that, there is this different composition within the two phases. The hydrogen never disappears. This could be like a geometry thing, as I was explaining. You don't expect to find many objects exactly like Janus because it's a very specific geometry, which you have like really seeing one phase and the other phase. So it's okay that one of the elements never disappear, but here you're also seeing that the magnetic field is changing quite a lot over the surface. What could be happening is that the splitting disappears because maybe the magnetic field is lower than a megagauss. So it goes from 8 to lower than 8. Or it could be that the magnetic field on the other side is so changing so quickly that the wings gets completely washed out because you get just different contribution from different strengths. So it could actually be high. It could be either lower or higher on the other side. But this one clearly shows that there is magnetic field in this object. And it also looks like the composition is varying on its surface. So yes, I mean, this could be an indication that indeed stars like Janus have magnetic fields. And this could be another object like that. I have to. This is new one just discovered, so it's gonna take me some time to figure this all out. A way to check what's going on in terms of magnetic field is taking polarimetry, spectral polarimetry, which can also be useful. Janus, unfortunately, is too faint to get polarimetry. You need bright objects, but the other ones that I found, you can take polarimetry like this one, for example. To figure out exactly what's going on with the magnetic field.
The broadening of these lines is mainly due to the rotation of the star, or no?
The broadening. So first of all, these are massive white dwarfs.
Okay.
So a little bit comes just from that. The lines are broad, from just surface gravity.
Right.
They're hot, and so the lines are quite weak. But the lines are also weaker because of the magnetic field, I think, because they're just weaker. Like if there was this paper that just came out from Hardy, from the Montreal group, that analyzed hundreds of magnetic white dwarfs and found that in many, many cases, magnetic white dwarfs have weaker lines that you can get, compared to the temperature. And then they're broadened by the magnetic field itself because, the magnetic field is changing on the surface. And so those lines, get puffed up by the fact that there's, they get, you have contribution from different parts of the surface where the lines are slightly moved. And therefore they get either broadened or even washed out.
Right. Thank you. And there is a question by Chico Jablonski. He left it written here. Could the Janus be a non-eclipsing binary with one white dwarf being a hydrogen and the other being a helium-1?
Yeah, I think Elizabeth already asked that. It cannot be because at 15 minutes you would have like strong Doppler shifts that are not seen in the light. But also because the light curve is sinusoidal, and if it was really the two eclipsing one, you would have like obvious eclipses in the light curve.
Thank you very much. I'll make a very short question, my last. And about the disks, you talked about a little bit in the beginning, that they are inferred by the excess of infrareds. It's possible to infer some geometrical properties of these disks, the extent with the existing data?
I mean, there's been a lot of work on disks, on white dwarfs in the field. There's a person at Gemini Observatory. She's taking a spectra in the infrared of these disks, for example, and there's sometimes emission lines from which we can figure out some geometric properties. It's a bit hard because I don't think it's a very well constrained problem. I think there's another researcher, Nicola Gentile Fusillo, who found a disk around a white dwarf, like with several rings, I think, because he saw several different emission lines at different velocities. So there are a lot of these studies done on field white dwarfs. But for these ones, for the ones that I would find in the globular cluster, I'm just getting an infrared excess. So I could get a sense of like maybe the temperature of the disk or the size of the disk, but not much more. Also because I only have 2 infrared filters. It would be interesting to get maybe some if the disks that I find are bright enough, it would be interesting to get some spectroscopy with JWST of them. And I think that would be interesting, maybe next cycle.
Very interesting. Maybe there is a little bit of a reflection in the optical and then some polarization. Is it possible?
What do you mean, reflection?
Polarization by reflection, the disk from the optical, if there is some enough ionized material.
I don't know if anyone sees the polarization of the disks. I have no idea.
Okay. Well, let's think again, Ilaria. Thank you very much, and thank you for attending all the questions. It attracted a lot of curiosity. The data are very intriguing, and thank you for sharing with us.
Thank you. Thank you for the great questions.
Okay, thank you. Now everyone is invited to a coffee break by the side of the auditorium. Unfortunately, you cannot attend our coffee
Enjoy
break.
Your coffee break.
Okay, thank you. Bye-bye.
Bye-bye, thanks.